to this organizer and for inviting me to share my little knowledge on this star polynomial and how to use it to determine the dominating uniqueness of graph. Actually, throughout my research career, I spent most of my time working on chromatic polynomial and also various graph labeling problems. And it was in 2016 when I was invited to give a talk in China. I suddenly decided to try something new. And when I look at the existing result on dominating uniqueness of graph, then suddenly I noticed that I am able to come up with this new idea that I should introduce the concept of star polynomials and use it to determine the dominating uniqueness of graph. And so here I have this presentation today. So here is a simple outline. And I'm going to start by talking about the basic knowledge on dominating set polynomial and also a little bit about chromaticity of graph. And before I go to dominating uniqueness of graph. So bear with me if you think that what I'm going to present will be something the previous two speakers have spoken about. And then I'm going to talk about star polynomial and how to relate them to domination polynomial and use it to determine the dominating uniqueness of various types of graph. And of course, I will have some interesting problems and conjecture also. So as usual, I'm going to let G as a graph in order n and size m, and G VH will be the joint of G and H, and G plus H will be the disjoint union of G and H. So the MG is the disjoint union of M copies of G. Yeah. So as we have seen, a subset S of a vertex set V is a dominating set of G if every vertex not in S is adjacent to at least one vertex in S. And the minimum size of a dominating set is the domination number of G, usually denoted by gamma. So of course, if G has a vertex of degree n minus 1, then gamma is 1. Recall that I always assume that G has order n. Yeah. And for cycle graph, we can also easily get the domination number of it. So we shall call a dominating set of size I and I dominating set of G. So the DGI become the number of I dominating set of G. Yeah. And it's easy to compute the DGI if G is a complete graph. I believe some of us today actually may not know very well about this concept of dominating sets and domination polynomial. And so I'm going to explain with this in more detail using this simple graph G here. So here you can see here gamma is 2 because there is a dominating set of size 2 given by the vertices A and E. Yeah? Okay. And then in a similar way, you can easily find there are 13 dominating set of size 3. Okay. And there are 14 dominating set of size 4 and 6 dominating set of size 5 and only 1 dominating set of size 6. So with this, we can define domination polynomial of graph G as the sum of DGI times x power I from gamma to n. So in our previous example, the graph G that we have seen just now has this domination polynomial given by this expression here. And of course, for complete graph and empty graph, it's easy to find them, the domination polynomial. So probably all of us know that this concept was introduced earlier in 2000 with the coefficient in reverse order. And if we want to know more about the application, we can look at 2 papers here in 2012 and also 1991. This is more about dominating sets. Before I go further, let me talk a little bit about chromatic polynomials. We say a proper vertex coloring of a graph G. We say a coloring is proper. A vertex coloring is proper if we have no adjacent vertices getting the same color. So if we want to color the vertices of a graph G using Amos lambda colors, then the number of ways is a chromatic polynomial. And again, finding the chromatic polynomial of complete graph and empty graph is just a simple process. So we say two graphs are chromatically equivalent if they have the same chromatic polynomial. So back in 1978, Chow and Whitehead already introduced the concept of chromatically unique graph. He said that G is chromatically unique if PG equal to PH implies that H is always isomorphic to G. Yeah. So before 2015, we have many papers published in this area, but after 2015, very few papers are available actually. So as an analogy, in 2012, Syed Ali Khani introduced the concept of dominating uniqueness that we have seen just now actually, as presented by our first speaker. So we say two graphs are dominating equivalent if they have the same dominating polynomial. And we also say a graph G is dominating unique or D-unique if DG equal DH implies that H is isomorphic to G. So that the dominating equivalent class of G is the graph G itself, if G is dominating unique. And by a simple direct calculation, we can see that the graph P4 and the graph 2P2, they have the same domination polynomial. And if you consider all other different graphs of order 4, we can also easily conclude that no other graph of order 4 must have the same domination polynomial. And so it means that the D equivalent class of this P4 is a set of P4 and 2P2. Okay. So this is the first result obtained by Ali Khani. They say that, or they prove that if G is a graph of order n with a vertex v of degree n minus 1, then G is D unique if and only if the graph G with a vertex v of degree n minus 1 deleted is also D unique. And then later on, we have also this result in which the cycle, every cycle is D unique. And also in 2015, we have this result that complete multi-partite graph is D unique if and only if every partite set is of size at most 2, or the difference between any two different distinct partite set, the size must have a difference of at least 2. Okay. And then also actually Ali Khani and Ping also proved that out of all the cubic graph of order 10, 9 of them, they are dominating unique. Okay, so these are 9 of them. And in general, until today, as far as I'm concerned, or as far as I'm aware, very few results are known, or I mean, very few new results are known. For dominating equivalent graph, Ali Khani also proved that these two family of graph are D equivalent. So one is a path and another one is a path with one certain edge added. Yeah. They also show that these 3 pairs of non-isomorphic graph have the same domination polynomial. Okay. So one of the newer paper on this equivalent class is in 2016 year. Now, just now why I talk about chromatic polynomial, it was because my idea was actually coming from this concept of this adjoint polynomial introduced by R.Y. Liu in 1997. He studied the adjoint polynomial of a graph and the uniqueness of the graph And it turns out that the conclusion can be used to give new graph that are chromatically unique. So actually, he studies the adjoint uniqueness of a graph G and use it to get many new graph G complement that are chromatically unique. So motivated by this, I also decided to try to work on the complement side of a graph. And so I introduced this concept of star polynomials. So before I look at the definition, I would like to introduce this subset of size I is an I subset, so that if G has n vertices, I'm going to let SGI to be the number of K1I subgraph with distinct n vertices in G. Yeah? So K1I is just the star graph with I isolated vertices. That's why I decided to call this polynomial star polynomial. Note that SG1 actually is the number of non-isolated vertices of G. And if I is greater than the maximum degree of G, then SGI is 0. And moreover, isolated vertices play no role in computing SGI. So if we look at the graph G that we have seen just now, so SG1 is 6, the order of G. For SG2, we want to find the number of K12 subgraph with distinct n vertex sets. So you can see here the vertices A, B, C, and the vertices B, B, C. Both of them are K12 subgraph, but they have the same n vertex sets. The vertices B and C. So these two are counted as only 1 in getting the actual value of SG2. In a similar way, you can see that there are exactly 5 different K12 subgraph with what we call having distinct n vertex sets. For SG3, it is equal to 1 because there is only one vertex of degree 3 and there's no SG4, SG5, SG6. Okay, because the maximum degree is 3 only. So now we can define what we call the star polynomial, similar to what we define this domination polynomial. So it is the SGX, which is the sum of SGI times X power I. So from what we have computed just now, you can easily see that for this graph G, the SGX is 6x plus 5x squared plus x power 3. And if we add in as many isolated vertices as possible to this graph, to get the G plus ON here, then we still get the same star polynomial. Okay. So note that every I subset of SGI, the I vertices do not have common neighbors in G complement. So they do not form an I dominating set of G complement. With this, we can easily get this theorem 2 here, in which DGI is n choose I minus the SG complement I. Okay? And DGI is equal to n choose I if and only if I is greater than maximum degree of G complement. So if we know how to compute SGX, then we can easily find the domination polynomial of G complement and also the domination polynomial of G complement joined with complete graph Kn. So here is the example for the same graph G here. Okay. And the domination polynomial of G complement can be obtained easily. Similarly, for G complement joined complete graph Kn, you can also find the domination polynomial easily. So this concept of star polynomial gives us a very good tool to compute the domination polynomial of dense graph, because the complement is a sparse graph with few edges and easy to compute the star polynomial. So with this, we are able to also define the star equivalence of graph. And we say two graph G and H are star equivalent or S equivalent if they have the same star polynomial. Okay. However, note that just now I already point out that every graph G and the G, if isolated vertices, must have the same star polynomial. Therefore, the S equivalent class of G is of infinite size. And because of this, we are not able to immediately define star uniqueness of a graph. So what I do is here, I let G star to be the graph obtained from G by deleting all the isolated vertices. So now I can define star uniqueness of a graph G. I say a graph G star is star unique or S unique if the SH equal to SG star implies that the graph H star is isomorphic to G star. In other words, G star is S unique if and only if the star equivalent class of this G star is the set of the graph G, possibly with some isolated vertices added. Moreover, we can easily see that two graph G and H have the same domination polynomial if and only if their complement must have the same order and also same star polynomial. If and only if the star of the complement, okay, have the same star polynomial. In other words, G is D unique if and only if G complement star is S unique. So this means what? This means that G star is S unique if and only if the complement of G star drive a complete graph Km is D unique. Okay? So we are able to now make use of this star uniqueness of graph to determine the dominating uniqueness of many dense graph. So before I go further, I am going to introduce one more type of graph that I am going to denote it by G triangle or G delta. Is the graph obtained from G by deleting all the vertices U such that du is of degree n minus 1, which is adjacent to all other remaining vertices. So note that the complement of G triangle is actually the G complement star. Okay. So here, as a visualization, if this is the graph G, then this is our G triangle with the vertex D deleted. And this is the G complement. And this is the complement of G triangle, which is also the star of G complement with the vertex D deleted. So now we are able to get our first main theorem here. If G is D unique, then the G delta joined by Km is D unique for every n. So the proof is quite straightforward and short actually. A good implication is that the theorem 1 that we've seen just now at the beginning is actually now a special case of this theorem 3. Okay. And we are also able to get a new theorem regarding the D-equivalent classes of graph G here. So if the D-equivalent class of G has n vertices G1 until Gn, okay, then actually the G1 delta complement up to Gn delta complement, all of them have the same star polynomial. Okay. Consequently, the D-equivalent class of G joint Km is also the set of G1 joint Km up to Gn joint Km. So now, making use of what we have already known about D-equivalent classes of graph, okay, we are able to come up with new results in which, okay, back in 2010, it was proven that this graph Pn and this Pn prime, actually they form a D-equivalent class of graph. And For complete multipartite graph, KRN here. So this is a complete R-partite graph with every partite set of size n. Okay. The D equivalent class actually is a set of this graph JRNT. Yeah? So the definition of JRNT is here. Is the joint of many copies, I should say T copies of Kn Cartesian product K2, and then join with this another R minus 2T partite graph, complete R minus 2T partite graph, in which if T is 0, actually JRN0 is the graph KRN. So we also know that for cubic graph of order 10, we have these three different classes of D equivalent graph. These results are obtained by Alekani. So using our theorems 3 and 4 just now, we are able to get many new results. Okay? For example, we already know Cn is D unique. So now Cn joint Km is also D unique. Similarly, for this complete multipartite graph, joint Km, under the same conditions. And of course, also the graph GI that we know they are D unique just now. Remember, GI are those cubic graph of order 10. Okay. So similarly, for D equivalent classes of graph, we can have new equivalent classes now. Note that the cycle graph Cn joint K1 is actually the view graph of order n plus 1. And because Cn joint Km is D unique, therefore we immediately conclude that the view graph is D unique. So one interesting problem here is it possible to find necessary and all sufficient conditions so that if H is D equivalent to the joint of two graph G1 and G2, then H is actually also the joint of two graph H1 and H2. Okay. From now on, whenever possible, we are going to assume that a graph is connected without isolated vertices, unless stated otherwise. This is another result obtained by Alekani on regular graph. I think he also mentioned about this theorem just now. So suppose H is a S regular graph in which every two vertices U and V, they have distinct a close neighborhood. So now if DG equal DH, we can conclude that G is also an S regular graph. So we have a similar result on star polynomial for regular graph. So suppose H is an R regular graph where every two non-adjacent vertices have distinct open neighborhood. In other words, H does not contain a K2R subgraph. If UV form the partite set of size 2, probably R here is a typo, I believe. It shouldn't be an R probably. Okay. Then if G and H are the same star polynomial, then G is also an R regular graph of same order. Here I'm assuming that we don't consider all the isolated vertices. So using this, we can immediately get this result on one regular graph. So the one regular graph is S unique. In other words, the complete graph with a perfect matching of A edges deleted is D unique. And so the joint of this graph with the complete graph Km is also D unique. And how about two regular graph? For two regular graph, we also determine the S equivalent class completely. Here is a small typo. The equal sign here should be the equality for both left-hand side and the right-hand side. Okay, The proof is not too long, but a bit tedious to explain. Sometimes we consider the SGI for small I and so on in order to get our conclusion. So using what we have seen just now, we are able to get this. The star equivalent class of C4 and also the D equivalent class of 2P2 that we have seen just now actually. So from the previous result, we can conclude that a two regular graph G is S unique if and only if G is the cycle of order 3, 5, or 7. And equivalently, the complement of this cycle joined with Km is D unique if and only if N is 3, 5, 7. And for any graph H, the join of H and the complement of cycle is not D unique if this cycle has order 3, 5, or 7. It's not order 3, 5, or 7. How about cubic graph of order 4 and 6? So for order 4, the only graph is K4, so it is S unique. For order 6, there are only 2 of them. The first one, if you look at the complement, is the C6 and is D unique. And so the complement, which is the original graph K3, Cartesian K2, the star equivalent class must be this graph K3, Cartesian K2, possibly with some isolated vertices added. And how about K33? For K33, we study the SG1, SG2, SG3, and so on. Okay. From there, we are able to argue one by one that the S equivalent class of K33 must be the set of the graph H, possibly with some isolated vertices added, in which H is actually the K33 itself, or with the most 4 edges of a C4 subgraph deleted, or it could be a K112 disjoint union with K2, or is the K24 with 2 non-adjacent edges deleted. Okay. Since G complement of this K33 is 2 copy of C3, what does that mean? So we get the D equivalent class of 2C3 must be the set of all the graph H complement for H obtained here. So what does that mean? It means that there are infinitely many 2 regular graphs that are not D unique. So determining the D uniqueness of 2 regular graphs still, I think, an open problem. And now we can look at cubic graph of order 8. For order 8, there are 6 of them here. I use direct computation to compute the star polynomial. And of course, using the 2 theorem just now on a regular graph, we are able to make conclusion that Hj is actually a star unique. If J is 1, 4, 5, 6, okay? And H2, H3, they form an S equivalent class. And the complement of this graph must be a 4 regular graph of order 8. And so immediately we get new results on D uniqueness and D equivalent classes of graph. Next, we can look at cubic graph of order 10. For order 10, there are, I believe, 21 of them. Yeah. So again, by studying the star polynomial of this graph one by one, and also by applying the theorem on what we call regular graph, we are able to show that, okay, if H is S equivalent to the graph J from 1 to 16, then H is also out of this graph. More precisely, we managed to show that the graph Gj is star unique if J is this 4, 5, 6, 14, 15, 16. And G1, G2, G3 form an S equivalent class of graph. G7, 8, 9 also, and then G10, 11 also, G12 and 13 also. And the complement of all this graph must be a 6 regular graph of order 10. So we also get new result on the uniqueness of this, the complement of this graph. Okay. Now, note that if you want to determine the S uniqueness of G17 to G21, okay, using the theorem on regular graph, we are not able to make conclusion that they must be one of these graphs. Okay. So that means what? That means we have to check all non-regular graph of order 10. Okay. So this is a very tedious task. And so I decided not to continue. And of course, we can see that the graph G21 is not as unique because it has a K33 component. Yeah. Okay. So the problem here is determine the S equivalent classes of G17 to G21. If we look at the star polynomial of this 4 graph here, 5 graph here, the coefficients are unimodal. Okay, unimodal. So this leaves us an interesting conjecture later on. Yeah. So now what we have is not every 2 regular graph are what we call dominating unique. Yeah. Okay. In fact, every 2 regular graph G that has no C3 component satisfy that every 2 vertices have distinct close neighborhood, the theorem find. Yeah? So what does that mean? That means that if G is such a graph, if G is such a graph, and H has the same domination polynomial as G, then H is also a 2 regular graph without C3 components. Okay. However, if we have 2 C3 components, then the graph is not D unique. So we can have this conclusion that every graph with 2 C3 components is not D unique. But characterizing the D uniqueness of 2 regular graphs is still a big problem, I believe. Now, what I would like to conjecture here is that every 2 regular graph is D unique even only if it has no C3 component. And then we actually also look at many biregular graphs. The first one is the disjoint union of A copies of P3. We managed to show that it is S unique even only if A is 1. So from there, we also get the equivalent classes of the complement of this graph, joined with what we call this complete graph. For a small number of A, we are able to list down the D equivalent classes one by one. Here, there is another typo here. There should be a complement over this plus 3P2 here. And we also look at the S equivalent classes of path Pn. And we managed to also solve the problem completely. As a corollary, the path Pn is S unique if and only if n is 2 or 3. Okay. So graph G is not D unique if G complement has a path Pn, n is at least 4, or it has a C4, or it has a path and a cycle, or it has 2 cycle components. This is based on the result of theorem. And later on, we also study a spider graph. And we managed to show that a spider graph is S unique if and only if it is the graph K1M, or M at least 2. So this is also a star graph actually. And the KT grooving of a complete graph on T plus 1 vertices and T plus M vertices is also D unique. So I had this problem and conjecture. because we already know that P2 is D-unique, but the 2 copy of P2 is not D-unique. So we want to ask a question here. Find necessary and all sufficient conditions such that the disjoint union of 2 D-unique graph is also D-unique. And particularly for half, we know that P4, PNN is 0 mode 3 are not D-unique, but P2, P5 are D-unique. So my conjecture here is Pn is D-unique, even only if n is 2 mode 3. Now, in preparing this slide, actually, I found out that in 2017, one researcher already come up with a paper. They give the connection between adjoint polynomials and independence polynomials. So I would like to suggest this problem. So find a connection between star or domination polynomial and other polynomials, particularly if possible between adjoint polynomial or between chromatic polynomial and so on. Now, if you recall all the star polynomial of the graph that we have computed, they are all unimodal. So my conjecture here is that for every graph G, the star polynomial is unimodal. Okay, there is an interesting remark given by Marcus Dot. After I submitted my paper back in 2016, I think. So he wrote to me saying that our star polynomial is actually equivalent to the neighborhood polynomial defined by Brown and Novosibirsk in 2008. The only difference is a small -1 here. But they didn't define it to study the dominating uniqueness of graph. Anyway, if we read the results in that paper carefully, we are able to make this conclusion that the complement of all trees having the same degree sequence are D-equivalent. So determining the D-equivalent classes of all the trees of same degree sequence is another very interesting problem. Now, I would like to take this opportunity to introduce to everyone here new families of graph. As I mentioned earlier, I spent so many years on graph labeling, especially for the last 5 years, in which I spent almost all my time working on local antimagic chromatic number. And I have come across so many types of graph, but none of them is what I'm going to introduce now. So for a graph G of size n, the bijective labeling F that label the edges from 1 to n induces a vertex labeling given by the sum of the incident edge label. This labeling is local antimagic if no two adjacent vertices get the same induced label. If we assign the induced vertex label as the color of that vertex, then we know that F induces a proper vertex coloring. And the smallest number of distinct induced vertex color is called a local antimagic chromatic number of G, denoted chi-LAG. And of course, it's easy to see that chi-LAG is at least chi-G. And although a cycle may be bipartite, and every path is bipartite, yet actually they have chi-LA equal to 3. Okay? So over the last few years, we have also determined the chi-LA of many regular graphs up to order at most 8. Yeah, these are some of the graphs, regular graph of order at most 8. And we completely determine the local antimagic chromatic number. Now we have many papers published also. What is more interesting is this. In my latest investigation, about 3 months ago, when I try to construct a new types of graph, so coincidentally that when I draw them, the graph that I get is something like this love shape or heart shape. Okay, and the graph that I construct must have order at least 9, and the order must be odd. And for order 9, I can only get exactly 4 non-isomorphic graph. And I was able to show that all of them have local intermediate chromatic number 3. So how to construct this graph? First of all, I start with a path given by the outside edges here. And then I add in another path of same length. But now, first I start from the first vertex on top here, and then I must go to the next vertex with even subscript. So this is U1, U2, U3, U4, U5, U6, U7, U8, U9. So I go from U1 and then go to even subscript and then odd subscript, and then even subscript and then odd subscript, and so on until finally I reach the last vertex here. And not only that, I need to add another 4 edges from this first vertex and the last vertex to 2 distinct vertices of odd order. For example, here, V3 and V7. So in the process, I cannot have multiple edges. Okay? So if the order is 9, I only can get these 4 graphs. They are not isomorphic. If larger order, I can get something like this. And of course, if the order is getting larger and larger, I can add in even more paths. Just now, for this example, I only use 2 paths. So when the order increases, I can add in more and more paths to get more and more complicated graph. And actually, the best result is I can show that all such graph must have local intermediate chromatic number 3. So in other words, I can send everyone in the world one of such love graph. Okay? And all of them will get non-isomorphic one. And all these graphs of different orders, maybe same order, we have local intermediate chromatic number equal 3. So suddenly it comes to my mind that I decided to name this family of graph as love all in universe graph. And so surprisingly, when I look at the initial LAU, it formed my surname. So I didn't purposely name it using my surname actually, but it's so coincident, yeah. And then I also found that I can also make some modification so that I can use at least 2 different love graph to construct new connected graph, something like this. This is just one possibility. And again, it has local intermediate chromatic number equal to 3. So I decided to call it circular graph. And more generally, I can even have a disconnected graph in which the component is a love graph or a circular graph. Again, this disconnected graph has chi LA equal to 3. And so I decided to call it generalized circular graph. And so probably the last open problems for everyone here is, let's study the properties, the various properties of this Lau graph, circular Lau graph, and generalized circular Lau graph in terms of the chromatic number, in terms of the chromatic polynomials, I should say polynomial, in terms of the total or Roman domination number and the polynomial, and also the independent star polynomial, and also many other graph parameters, like the magicness, the anti-magicness, and also the Sudoku number that actually we introduced probably about 1 year ago. It was not too new actually. Someone has studied something similar actually after our submission. They only found out. Okay. So here I have these references of what I have presented today. And finally, give me a few minutes to talk about this picture. So coincidentally, this picture was taken on October 26th, the day of my birthday. I was having a trail run. And in the evening, I suddenly come across this very majestic view of a love shape created by the sunset and the trees. There are two trees here actually. Okay. And so happened that after I finished my run, the total distance recorded was 10.26 kilometers, exactly the October 26th. So what a coincidence for me. Huh? I always consider myself very, very lucky. So with love, thank you very much for your attention.
Okay, thank you so much, Lau, for your nice presentation. I really enjoy it. Is there any question, comments, remarks? Lau, you know, we characterize the D equivalent classes of pass for n congruent to 0 with modulus theory, you know.
Okay.
And recently Brown and his student proved that our result for n congruent to 0 is true also for another cases, and this problem has solved.
Oh, I see. Thank you
Yes,
for telling me. Huh?
yes, the equivalence classes of pass is exactly the same that we found for n congruent to 0. So, and another question that I think you thought you uh, talk about two regular graphs and consider just circles, yes?
Two regular graph and
When you consider two regular graphs,
yeah,
if you must consider cycles,
circles, yes, yeah, cycles, yes, yeah.
and you could. But I think you told us that the S equivalence classes of cycles is open.
No, for S equivalent classes of cycle is completely solved. But for D equivalent class of is open, as far as I am aware.
For D equivalence, I think is solved. I think for D equivalence classes of cycle, we do not have any problem.
I mean, two regular graph, not just a cycle.
Oh, two regular graphs are disjoint union of cycles.
Yes, yes.
Okay, so if one of them is unique, then it's okay for D equivalence. No. Yes, you are right. You are right. Okay.
Yeah.
Thank you.
Yeah.
Okay, is there any question? Remarks? Hamid, do you have any question? Okay, thank you
No,
so
I
much
have a
again.
question.
Okay.
I would like to thank you, Mr. Lau, for this presentation. I wish you all the best, Lau.
Yeah, thank
in
you
your
for
research.
inviting.